All right, today, section 7.5, our objective is to be able to solve exponential and logarithmic equations and inequalities. Now, there's not a lot of new things today, a couple formulas, but then we'll go through a lot of examples on these. So, first thing, which we've kind of worked with before, that if we can get the same base, which we've turned a lot of things into the same base, remember, if the bases are the same and it's equal, then that would mean the exponents have to be the same. So, we did a lot of that with like 2 to the x equals 16, and then we wrote it with the same base. So 2 to the x, we changed 16 into 2 to the 4th power, and therefore we know that x equals 4. So we did that a lot on the last two sections of this chapter. The next thing we're going to run into, if we can get it so that we have if log base x of a equals log base x of b, in other words, if we can get down to a single logarithm on each side of the equation, where the bases are the same, then we know that we can just, the only way that can be true is if a equals b. So basically you're just eliminating logarithm on each side and just going with that a is equal to b. Really important to understand, where is the variable in the equation? If the variable is in the exponent, then we have to solve using logarithmic form. Okay? If the variable is not in the exponent, then we can solve using exponential form. So we really need to look at these and determine where that variable is in each question, and then we know what format to set it in to solve. So an example, first one. 8 to the x is equal to 2 to the x plus 6. Now we could do mental math like we did before, because in this case we could change it to the same base, and we could write 8 as 2 to the 3rd. And so this would be, remember, a power to a power we multiply. So that's 2 to the 3x equals 2 to the x plus 6. Now we're using this rule here, that since the bases are the same, we can drop those and we can just solve the equation 3x equals x plus 6. And then solve that. Subtract x. And so we get 2x equals 6. And divide by 2, so x equals 3. So that would be one way we could solve this. It works nice if the bases are the same, but in most cases that's not what happens. So if we go back to our rules and we say, where is the variable? Well, the variable is in the exponent. So what we're going to do now is use the reverse of this rule. Since we know they're equal, we can add the log and make it any base we want. And since the calculator we can do base 10, what we're going to do is take this equation and add logarithms to both sides. And put it in that format. Now this is where we're going to start using the rules that we've been building on this chapter. So remember, we can move the variable, if it's in the exponent, we can move it out front. So that would become x log base 8 equals x plus 6 log 2. And now here is just kind of an individual preference. We can do these on the calculator. So if I call the calculator up, we can figure out what log 8 is. So log 8. And we can insert 0.093. And I'll have you round these to to 3 places. It'll give us fairly accurate answer. And then we can do log base 2, or log base 10 of 2, so log 2, and get 0.031. And now we can just solve it algebraically. And so you could, this is 0.093x equals, distribute that. And so 6 times 0.031. 0.186. And then we can solve that. Subtract 0.031. Variables on the same side. And so we get 0.062x equals 0.186. And then divide that by 0.062. And we get 3. So we got the same answer that we got here. It's just another way to do it. Now, personally, you can change these logarithms as soon as you get the chance. But what I like to do when I'm doing these is leave it as a logarithm right here and just go, now I'm going to divide by log 2. So I'm going to take this. That way I don't have to distribute such a large decimal, or these little decimals. And so now I just do it on the calculator. Log 8, remember to close the parentheses, divided by log 2. And it gives me 3 right there. So I get 3x equals x plus 6. Subtract x, 2x equals 6. So x equals 3. So by leaving it in the form of a logarithm as long as possible, it makes it so I don't have to work with all these decimals as I go through. But totally up to you. Sometimes you do need to put the decimals in early, but again, I would most of the time do it that way. So let's look at another one. X minus 2 equals 200. So again, the first thing we ask ourselves is where is the variable? In this case, it's in the exponent. So I'm going to do logarithms. So I go log. Again, we're going to do base 10. Equals log 200. Again, I could change this to a decimal right now, but I'm going to wait. The power, remember, we can bring in front of the logarithm, so I can rewrite this. X minus 2 log 5. And we get the logarithms on the same side. So now I'm going to change that to a decimal. So it was log 200 divided by log 5. And we get 3.292. Alright, so now we're down to x minus 2 equals 3.292. We add 2 to both sides. So x equals 5.292. So again, as we go back through this, we decide where the variable was, it's in the exponent. We add the logarithm to both sides, move the exponent out front, and then Get the logarithms on both sides, get the decimals, and then it's solving algebraically. If in your book you look on page 523, there's a story problem. And that story problem says, you can choose a prize of either a $20,000 car, so they're going to give you a choice, a $20,000 car, or you can get a penny on the first day and double that. 1 penny on the first day and double that to 2 cents on the second day, and so on for a month. So now you're going to start at a penny, and you're going to double that every day. Okay? And they want to know, when is this going to be more than that? So they set up the problem. To get the same base, we're going to put this. So on the second day, I would have 2 cents. And so then this would be n minus 1, because on the previous day, remember, if we put in on the first day, 1 minus 1 is 0, and anything to the 0 power is 1, so that would be 1 cent on the first day. So we're going to have 1 cent, and we're going to double that every day. Now they want to know, when is that going to be greater than $20,000? Now since this is in cents, I'm going to change this to cents. So that'd be 2 million pennies. So we want to know, what day is this going to be greater than this? Well, again, we look at it, and our variable is in the exponent. So I'm going to add a logarithm to both sides. Log 2 million. Bring the exponent out front. Log 2 million. Move the log to the other side, divide by log 2. And so we get n minus 1 is greater than, and now we bring out the calculator, and we go log 2 million divided by log 2, and we get 20.932. Add 1. So it'd be 21.932 days, but you can't have that, so we'd have to go up. And when n was 22, so on the 22nd day, you would get more than the $20,000 car. All right? So again, you set up the equation, variables in the exponent, so we add the log of both sides, and then we go through and solve it. Next example. I'm going to try and give you a lot of what you're going to see on this assignment. So, log base 3 x minus 5 equals 2. So if you ask yourself, where is the variable? Now in a logarithm, remember our exponent is over here. So our variable is not in the exponent, it's in the answer, so we don't want to use logarithms. Now, if you're looking at the book on how they do it, they do this a little, I wouldn't do it this way, but I want to show you so if you see it, so kind of ignore this, we'll come back to it. The book will do this. So they'll take this and they'll say, well, let's get rid of this logarithm by moving it to the exponent. Oh, 3 to the second. So what they've done is they just put this to the exponent. Since they're equal, then it should be the same. And then they use the rule that tells us, remember, if this base is the same as this base, that cancels. And so they get x minus 5 equals 9. And it's fine to do it this way, it doesn't make sense to me that it's the best way. Because we know since the variable is not in the exponent, we want to switch this to exponential form. And if we change it to exponential form, we get 3 squared, remember base, exponent, answer, x minus 5. So we don't have to go through this process. So this is what I recommend doing, but the book, when they show their examples, they do it this way. So we get 9 equals x minus 5. We add 5 to both sides. And so 14 equals x. And so that's the way I'll do them as I show the examples on here. Up to you which way you want to do it. But this is the way the book shows it, but I would just switch it to exponential form. Okay, a little more complicated now. Again, we want to look where the variable is. And the variable is not in the exponent. Remember, our exponent with logarithms is over here. But what we do have to do is we have to get this down to a single logarithm. And to do that, we know that subtraction is division. Remember, we have the rule that says log whatever that base is. If these bases are the same as subtraction, I can write it as a single logarithm, same base, m divided by n. Well, since there's no base given, these are base 10, and so I can rewrite this log 45x divided by 3 equals 1. Now, because the variable is not in the exponent, I switch it to exponential form. Remember, since there's no base given, it's base 10. So it's 10 to the first equals, 3 goes into 45 15 times. And so we get 10 to the first is 10. And we divide by 15. 10 15ths, which reduces to 2/3. So our answer is 2/3. So when you have more than one logarithm, if we can get it down to 1, or if you can move it so you have just a single log on both sides, then you can get rid of the logarithms using this rule. And if I get a single log on both sides, but you can't have anything outside it, you can't have anything multiplied in front, then you can just drop the logarithms. All right. Let's try this one. So log base 4 of x squared equals 7. So, run into a problem that we've had before. We can't just switch this to exponential form because of this variable up here. Well, we'll try it both ways and see if it works the same. So I could bring this variable out front. 2 log 4x equals 7. Get the logarithm by itself, so I divide by 2. So log base 4 of x equals 7/2. And so this would be 4 to the 7/2 power equals x, and we can just type that into the calculator. 4, again I have to put that in parentheses, 128. Okay? Now, I'd be interested, let's try it the other way and see if it still works. So if I just put it in exponential form here, 4 to the 7th power equals x squared. So if we take 4 to the 7th is 16,384. And then take the square root of that, You get the same thing either way. So either way works. I can move the 2 out, get the logarithm by itself, or I can just leave it like that and solve the problem. So both ways work. All right, the next example. Log x plus log x plus 9 equals 1. So again, remember, this is our exponent, so our variable is not there, so we don't want to work with logarithms. So I need to get this down to a single logarithm. So addition, remember, becomes multiplication. Change it to exponential form. So that would be no base, so it's base 10. 10 to the first equals, I'm going to go ahead and distribute that. X squared plus 9x. 10 to the first is 10. It's a quadratic, so I have to set it equal to 0. So I'm going to subtract 10. So now remember, quadratic, you could use a quadratic formula. I'm going to factor this into x plus 10 times x minus 1. And so our answers, again, you should check this. X squared, yes. Negative 10, yes. 10x and negative x gives me a positive 9x, so I know I'm right. So my answers are negative 10 and positive 1. Now here's where you want to check your answers, because remember, we can't take the logarithm of a negative number. And if I put negative 10 in either one of these, I get a negative. And so this would be an extraneous solution. Remember, one that works in the problem that doesn't work when you go back to the original. And so our answer in this case would just be 1. And one more example. Log x minus log 2 is less than or equal to log 75. So now this one, we have another extra logarithm in here. But that's okay, because as long as we can get to a single logarithm on each side, remember, we can drop the logarithms. So because these are base 10, subtraction becomes division. And now we use the rule that we originally had today, that if we have a logarithm of the same base, then we can just drop those. So now we multiply by 2. And we get x is less than or equal to 150. Now, one other thing, because it's an inequality, remember, x has to be greater than 0. We can't do logarithms of 0. It has to be greater than that. So we know that x has to be also greater than 0. So, your assignment for this section, page 526, numbers 9 to 25, the odds, 28 to 31, all. Remember, when doing these, examine where the variable is. If the variable is in the exponent, then we need to use logarithms. If the variable is not in the exponent, then we can go ahead and change it to exponential form and solve it. All right, that's it.